7, part 2, day 1. Really, I'm just going to run through this whole section today, and then we'll spend the next couple days going over specific examples of it. But I just think it's easiest to just kind of just tell you what the whole lesson is, and then we can go through and look at it, like I said, a little bit as we go through the rest of the chapter. So first thing, if I asked you, how many of you guys want to do chores? If I asked 100 kids, how many of you want to do chores? I would expect 0 out of 100 to say that they want to do chores. But what if I change the conditions, right? What if I change the conditions a little bit and I offer you something in advance? And what I'm willing to offer is 1 red penny. I offer you a penny and I say, hey, look, now do you want to do chores? I would expect the numbers to look something like this. I offered a penny. By the way, I have to have kind of control, right? So I offer a penny to half the kids. So half the kids get offered a penny and half the kids don't get offered a penny. And I want to see, does offering a penny affect whether or not people want to do chores? Is there an association? And that's really what this chapter is about. If we take two things and we look at them together, does the one thing affect the other thing? That's really kind of what this chapter is about. And I would expect it to look kind of like this. Half the people I offered a penny to, and those 50 people probably would still not want to do chores, even though I offered them a penny. The people I didn't offer a penny to, I still would expect to not want to do chores. So I would expect no one to want to do chores, but I asked half the people, right? So what we can do is we can see if there's an association. And the way we do that is we first of all, just ask everyone, hey, what's the probability of the first thing happening? So what's the probability that everybody wants to do chores? We ignore kind of what's going on here and we just go straight to the bottom. 0 out of 100 people want to do chores. So 0 out of 100 people want to do chores. That's 0%. And then, given the second thing, what's the probability of the first thing happening? So if I give you a penny, I'm giving you. So these are the only people I care about right now. Right? I compared this group of everybody to this special group that I offered a penny to. And it looks like my odds are 0 out of 50. So there's 0%. So what I would say is there's no association. That penny isn't changing anything as far as to whether people want to do the chores or not, right? So what if I conduct this experiment again, but this time instead of offering a penny, I offer $1,000. So let's see what would happen, I think, if I offered $1,000. So now we're seeing, is there an association between wanting to do chores and offering $1,000? So again, probability is the first thing happening. It looks like 50 out of 100 people want to do chores. Right? That's the probability of the first thing happening. What's the probability that everyone wants to do chores? It looks like it's 50 out of 100. Now, I'm given the $1,000. I only care about the people I offered $1,000 because I want to see if that changes anything. And I'm looking specifically at those numbers, and you can see it's 50 out of 50, which is 100%. And these numbers are different, so that means that there is an association. It looks like if I want to get people to do chores, I should offer them $1,000. Again, up here, the numbers were the same. There was no association. It looks like if I want to get people to do chores, offering them a penny doesn't help me there to get them to do that. So that's really what this chapter is in a nutshell. Is we're just asking everybody one question, and then we're going to ask a subgroup that same question and compare the numbers. And if they're the same, we'll say there's no association. That offering that didn't really change anything. But if the numbers are different, then we'll say there is an association. So you might want to write that in your notes because people often get that backwards. All right, let me go ahead and pause this and set up the next part of the video. Notes, conditional probability notes for this chapter, and it has some review stuff. And then down at the bottom, it has some new stuff. And again, this is really the entire chapter, or part of the chapter in a nutshell. And we're going to spend more time practicing this, but really here's kind of what we're looking at. And again, this review stuff is stuff we should already know. So creating a two-way table. So first of all, we have to know how to make a two-way table. There's 200 sophomores at a school, 80 boys and 50 students with a driver's license. 90 girls don't have a license. So things to remember. Two-way tables should have two distinct categories. such as like a spinner, like a 1, 2, 3, 4, 5, 6, a yes or a no, boy or girl, grade in school. We want it to be a very definitive, like on-off switch. You're a boy or a girl, or you have a driver's license or you don't. We don't want it to be muddied, like, on a scale of 1. Well, no, I guess we could go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But anyway, so it says if only one category is mentioned, it's a total. If two categories are mentioned simultaneously, it goes in the middle. And this is what I mean by the middle. So if they're going to put a number in the middle, they have to tell me if it's a boy or girl and if they have a driver's license, yes or no. If they just tell me it's a boy, it's a total. If they just tell me it's a girl, it's a total. If they just tell me they have a driver's license, it's a total. So let's go ahead and look back up here. So in this example, 200 students is a total. So there's 200 sophomores out of school. There's 200 altogether. There's 80 boys. It doesn't say anything about driver's license or not, so we have to assume that's a total. There's 50 students with the driver's license. It doesn't tell me if it's a boy or a girl, so we're going to go over here as a total. And there's 90 girls that don't have a license. Well, they mentioned both. They mentioned it was a girl and that they don't have a license. And now I'm just going to use algebra to figure out the missing parts, right? Well, this could be 50 and 0 or 40 and 10 or 30 and 20. So I can't really figure out what adds up to 50, but here this is obviously 150. So I just want to start where there's one unknown, right? Here 80 plus 120 is 200. Here 30 plus 90 is 120. And now I can go over here. This must be 20. Originally I didn't know, but now it's sort of figuring out. And again, add it all up. 20 plus 60 is 80. 30 plus 90 is 120. 50 plus 150 is 2. And then go sideways. 20 plus 30 is 50. 60 plus 90 is 150. 80 plus 120 is 200. You want to make sure that it adds up the whole way. So again, just some things to remember when you're creating your own two-way table. And now we're going to do basic probabilities. They essentially ask the entire population. So we're asking all 200 people, what's the probability of having a license? We would say 50 out of 200. And again, we're asking the whole population of 200, what's the probability of being a girl? We would say there's 120 out of 200 chance of being a girl. Now, unions and intersections, again, we did this. I know I'm going a little quick here. So all of this stuff goes back to integrated 1. This part right here was integrated 2. I can't remember if it was chapter 2 or chapter 3, but we did that this year. So it says intersection questions are AND questions, meaning that data must be in both sets. Union questions are OR questions, meaning the data must be in one set or the other. So for example, what's the probability of selecting a boy with a license, or a boy and a license? So they have to be a boy, these are boys, and they have to have a license. And again, if I'm saying it's an AND question, they have to do both things. So it looks like 20 out of 200. There's 20 out of 200 that are boys with a license. I'm going to need this eraser to be bigger. Okay, next. It says, what's the probability of selecting a girl or someone with a license? Well, here's girls. And here's someone with the license. Now think about it. It's saying or, and I know these are totals. So there's two ways I can do this. I can either say 20 plus 30 plus 90, right? And I get 140 out of 200. Or I can say it's 50 plus 120, that's 170. But I have to subtract this 30 because I counted them twice, right? I only want to count them once. So I would get 170 minus 30 is 140 either way. And again, hopefully you guys remember all this stuff, because this definitely all goes back to stuff that we talked about earlier this year, the ands and or questions. Again, I probably should pause this and make my eraser bigger. All right, it says, what's the probability of selecting a girl without a license? A girl that has no license. Well, here's a girl, and here's the people with no license. And it's an AND question, so I would say 90 out of 200. And then what's the probability of selecting a boy or someone without a license? So we will say a boy or someone without a license. And again, I can say 20 plus 60 plus 90 is 170. Or I could say 80 plus 150 is 230 minus 60 because I counted this twice and I get 170 again. All right, so on to the new stuff. Conditional probability. Conditional probability is the idea that probability may change as conditions change. Essentially, you're asking a probability for a subset of the entire population. So let's kind of take a look here. It says, given that someone's a sophomore, right? Given that someone's a sophomore, what's the probability of having a license? We already know that we're dealing with sophomore and that there's only 100 of them. So this is our condition. Our condition is that we're talking to a sophomore. I know there's all this data for freshmen, juniors, and seniors and totals, but they told us we're given a sophomore. So none of these people matter right now. The only people that matter right now are the sophomores. Only 10 of the sophomores have a license out of 100. No, if we asked what are the odds of selecting someone having a license, just in general, it's 140 out of 440. If we asked what are the odds of selecting a sophomore with a license, it would be 10 out of 440 because we'd be asking everyone, and we'd have to pull both a sophomore and someone with a license. However, we're given a condition. We know we're dealing with a sophomore. What are the odds that the sophomore has a license? Let me pause real quick. These are larger, so I can erase more quickly. All right, so given someone with a license, what's the probability of choosing a senior? So we know this person has a license. This is the only row that matters. Uh-oh, that didn't go well. Okay. This is the only row that matters. What's the probability of choosing a senior? It looks like it's 80 out of 140. This is our condition and our conditional probability that goes with it. All right. It says, given a junior, what are the odds of having a license? We're only talking about juniors. It looks like the odds of having a license are 50 out of 100. Given a freshman, what are the odds of having a license? It looks like it's 0 out of 150. And it's, by the way, it says, notice there are no freshmen with a license, so the odds are 0 out of 150. The concept that two things cannot happen at the same time is known as mutually exclusive. They both exclude each other. So the odds of a mutually exclusive event happening are 0. So the odds of being like in room 31 and in room 33 at the same time are 0. That's a mutually exclusive thing to happen. The odds of being in room 31 or 33, that can happen. All right, and then the other thing, and again, this gets into what we were talking about right at the beginning of the class, says checking for association is essentially checking to see if one parameter influences the other. For instance, if I ask 100 teens if they want to do chores, 0 out of 100 would say yes. If I offered 1 cent, I'd still get 0 out of 100 responding yes. This means there's no association as the numbers did not change because the money had no impact on the willingness to do chores. However, if I offered $1,000, I'd probably get 100 out of 100 responding yes. There would be an association between the money and the willingness as the money caused the numbers to change. So again, and I know we've kind of already talked about this, but you ask everyone a question, how many students have a license? And then you ask the subgroup the same question, how many seniors have a license? So let's try this real quick. Let's ask everyone, do you have a license? Hey, everyone, do you have a license? It looks like 140 out of 440 have a license. Which is, let's go ahead and do the math on this. 140 divided by 440, 32% about 32% have a license. Now we're going to ask a subgroup the same question. Hey, seniors, how many of you have a license? Hey, seniors, how many of you have a license? It's 80 out of 90. So, and 80 out of 90 is going to be 89% about. And we'd say, hey, look, these numbers are different, so there is an association. It says if they're the same, there's no association. If the numbers are different, there is an association. So there is an association. Being a senior makes you more likely to have a driver's license. So I hope that makes sense. Again, we'll spend more time with it, but you can kind of get a feel for where we're headed in this chapter. And to do a couple more of these, here's a survey. If you could have a new vehicle, Would you want a sports utility vehicle or sports car? So think about how useful this information might be if you're trying to sell cars, right? Like, hey, you're trying to sell sports cars. Should you trying to sell them to men or women? And then you sort of run these numbers, and it gives you an idea of what magazines or websites that you should be advertising on in order to be effective selling those cars. So this kind of information is really useful in the real world. And obviously it's useful in a lot of more things besides marketing. That was just the one example I chose. So are wanting a sports car and being a man associated? First of all, I would ask, who here likes sports cars? It looks like women prefer sports cars, right? 45 to 39. It looks like more women prefer sports cars. But if you look here, there's more women being in this poll. So I'm not sure. 39 out of 60, that's way more than half of the males like sports cars. 45 out of 180, that's way less than half of the females like sports cars. So just something to consider there. So anyway, are wanting a sports car and being a man associated? So first, we're going to ask everyone, what's the probability of the first thing? What's the probability of wanting a sports car? Hey, everyone, do you want a sports car? The answer is 84 out of 240. And 84 out of 240 is 35%. And then we're going to come back and say, hey, given that you're a man, we're only asking men, given that you're a man, what's the odds that you like a sports car? And it's 39 out of 60. So we'll go here and we'll say 39 divided by 60 is 65%. So is there an association? Well, those numbers are different, so I would say yes. There is an association. It seems like, according to this data, which, by the way, is probably fictional, that men prefer sports cars. If you want to sell a sports car, you should apparently find a man. All right. And what's your favorite sport? So there's a couple of examples here. There's example A and B. And now that we've done a few of these, I would love it if you guys would pause the video and try this for yourself to see if you can kind of answer if there's an association between baseball and being a woman and basketball and being a man. So first of all, are liking baseball and being a woman associated? So what's the probability of the first thing happening? What's the probability of liking baseball? It looks like 60 out of 150 people like baseball. That is 40%. So it says, given the second thing, given that you're a female, what's the probability of liking baseball? It looks like 45 out of 73. So 45 divided by 73 is 61% or 61.6%. So yeah, I would say there's an association. So yes, there's an association. Women are, according to this data, more likely to like baseball. All right, what about basketball and being a man? Are they associated? So first of all, let's do the probability of the first thing. What's the probability of liking basketball? It looks like it's 38 out of 150 people like basketball. So let's go ahead and divide that. We get 25.3%. And now, given that we're talking about a man, what's the probability that they like basketball? And it looks like it's going to be 22 out of 77. And 22 divided by 77 is 28.5%, so 28.6%. So is there an association? And the numbers are different, but barely. I would say a very weak association, right? I mean, here it's pretty clear if you want someone who likes baseball, you should grab a woman. If you like someone who wants a car, you should grab a man. A sports car, you should grab a man. If you want people to do chores, you should give them $1,000 and not a penny. But here, I mean, you're almost just as likely to get someone who likes basketball, whether you pull a man or a woman, right? Those numbers are not very different, but there is a weak association. So again, that's where we're headed in this chapter. I hope that makes sense. I know I went through it quickly. We're going to be doing it more as we go through this section, but I just want to kind of let you know where we're headed with this chapter.